Welcome back, everybody. It is Monday. That was our sneaky adventure. Always like that one. Give me a quick yes in the participants window if you can hear me okay, and a no if it needs some more adjusting. Cool. Okay. Everything seems to be good. So there's a few announcements here on the page that you should be seeing right now for AICHE. These will be posted. I'll post the same stuff on our Canvas page for today's lecture. So you'll be able to actually click on the links and stuff. You won't have to like scramble to write down any of these links that are on there. And naturally, everything's being recorded right now, so you can always check the video afterwards. Today and most of Wednesday, we're just looking at examples of plug flow reactors. Let me up the brightness on this side of my face. There we go. Much better. Oh, yeah, sure. John wants to make a quick announcement about Homework Solutions 1. So why don't you go for it, John? I think you can unmute yourself.
Yeah, sounds
Okay.
good. So just quick announcement on homework. Number 1 has a error in the estimated answer, mainly due in part to my own mistake in the solution. So the correct estimated answer should be in the ballpark of 650. I think currently it's sitting at 880. So that would be incorrect. The correct answer should be around 650 for part number 1, part A.
What are
Um,
the units on 650?
Liters, if I'm not mistaken. It's a unit
Okay.
of volume.
Okay.
And then the other parts are still correct in the ballpark.
Okay. Cool
That's it.
beans. So updated estimate for the homework problem 4.1. So
I'll also be updating that on Canvas during lecture. So
yeah, that sounds good. Can you throw I think I forgot to put the highlight in there before. Can you highlight it and say updates?
yeah,
Because I'm sure that I screwed up something too. So that way I'll have a space to do my own. All right, so more PFRs today and Wednesday. And actually, I think if you're looking at the numbers of the lectures here, I think I'm off by one. I think this is actually lecture 21, not lecture 20, but it's okay. It doesn't mean we have to repeat the stuff that we did before. So let's take a look at our example for today, which is going to be one of the more general cases of a plug flow reactor that we can deal with. And because it's more general, it's going to be only able to be solved through MATLAB. So what we're going to focus on today is extending our previous abilities with MATLAB for solving a single differential equation to being able to solve it multiple coupled differential equations all at the same time, because that's kind of what we're looking at for the majority of PFR problems. And so the problem that we're going to deal with is the one that I've posted on Canvas. I want to say straightforward in the sense that I'm not asking for anything bizarre, right? What I'm asking for is a plot of the molar flow rate as well as the temperature profile. So those will run across the total volume of the reactor, and it's 600 liters. So it's not bizarre in that sense, right? We've got molar flow rates and temperature profiles. We're not. It's fairly straightforward in that sense. The difficulty with the problem comes in because of the number of things that we have to keep track of. So first of all, we have two reactions, right? We've got one reaction of A going to a desired component. We've also got another reaction of two A's coming together and sticking together and then forming an undesired component. And so that's usually not a good thing. We don't like to have undesired components. The other thing is that an awful lot of this stuff is temperature dependent. So it is going to be an adiabatic reactor. At the moment, we're still worried about isobaric stuff. We will relax the constant pressure assumption later, I think, next week. We will relax that or towards the end of this week. But everything else is going to be a function of temperature because the system is adiabatic and therefore it's not isothermal. So the first K for the first reaction and the second K for the second reaction, those are both going to be functions of temperature. We've got our activation energies here, and we've got our reference temperatures here. I have deliberately chosen different reference temperatures for everything, just so that we can kind of see how those temperatures come in and how they compare to the actual temperature of the reactor. One simplification is all of the heat capacities are the same. Which is not unusual when molecules are structurally quite similar. Their heat capacities tend to be quite similar as well. So if for example, the A goes to D is just taking like a methyl group and rotating it around, those heat capacities will probably be somewhat similar. The 2A goes to U, it's probably less accurate as an accurate approximation, because if you glue two molecules together, the resulting molecule is not really the same as either of the other two. But we're just going to roll with it. And then our enthalpies of reaction are just given at two reference temperatures. So these were not calculated using an enthalpy of formation. Had they been used using an enthalpy of formation, these would have been at 298 K. But these are, somebody just told us what the enthalpies of reaction are at some temperature. And so we're just going to have to adjust those as we go. And then the feed, again, not anything particularly bizarre. We've got a little bit of, oh, actually a lot of A coming in at 5 liters per second, and it's coming in at 400K. There's nothing else coming in, so it's pure A. And then the last part that's tricky is that it's gas phase, right? So a gas phase one means we're going to need the ideal gas equation, usually in this form, to adjust the inlet volumetric flow rate to the outlet volumetric flow rate, or more specifically, as we're going to try to detail in a moment, it's not really outlet volumetric flow rate. It's how much does the volumetric flow rate change as you go down the length of the reactor or down the volume of the reactor. And that's what we're going to spend this class talking about, is how do we calculate these things, and what does it mean to use these equations within ODE 4.5? What is the thing that we are actually solving? And so that expression up here for V is the one that we use for gases. Had it been for liquids, it would have been a little bit easier. But the intent of using the gases was to kind of show you this is about as bad as it gets, and it's not terrible. The only thing that makes it worse is if we ever have to do pressure drop. And then we will not be able to assume that these last two quantities over here are equal, but we're not going to get to that until later. So right now we're dealing with an isobaric system, so let's get rolling. The first thing I want to do is review our assumption. Or sorry, not review our assumption, review our numerical approximation. So the general approach of a numerical approximation that we saw Monday, no, was it Monday? I think it was Wednesday that we saw this, like a Wednesday morning lecture. The numerical approximation divided a plot. So if we had a plot that looks like this, let's say that the real curve was the one in black. Oops, not straight line like that. The real curve was the one in black. Our numerical approximation would subdivide this into a series of chunks like this, here, here, and here. And then it assumed that it was connected by a straight line from here to here, another straight line here to here, another straight line here to here, another straight line here to here. And then it would calculate the area. Well, it didn't literally calculate the area, but if you wanted to calculate the area, it would be the area under these trapezoids, right? And that was our numerical approximation. And what we had said was, it's the form that we had used was fine to get started, but ODE 4.5 uses a much more advanced approximation than just a straight line and connecting points. The key idea, though, was that if we knew where we started this point, we could use that information along with the slope at that point to project where we're going to be at the next iteration of volume, right? The next volume element inside of our reactor. And so we can kind of piggyback, right? We can go starting from our initial condition and calculate this one, and then use our approximation to calculate this one, and then approximate this one, and then use that one to approximate this one, right? And kind of step our way along what was the volume of the reactor, right? We're interested in volume, and then whatever our dependent variable is, like moles or temperature or whatever. The equation that we had used for that approximation, which I'm using it in red, so I might as well keep it in red, simplified to something that looked like the new value of any dependent parameter. So yi new, right? Yi could be your moles or your temperature or whatever it needs to be. We had approximated that as equal to the value that we had at the old one. So I'm using yi to represent anything that's changing down the length of the volume. So moles or temperature or whatever. Take the old value and add to it the product of the slope. And the slope was estimated as the value of the derivative, dy dv. And we evaluated that at the old values of yi. And then we multiplied this by the size of the step that we took, so delta v. And in the previous lecture that we had, we did this for one component, right? Which was, or sorry, one dependent variable, like n sub a versus v or something like that. The nice thing about ODE 4.5 and numerical approximations in general is that they scale to more than one component very, very easily. The only difference is that we have to have a slightly different syntax because we're carrying around more than one component, but the general approximation doesn't change. And that's what I want to focus on today, because our example has 4 components in it. And so generally the way that we will abbreviate these is with a capital Y, which is not yield. It's just by convention, when we have more than one dependent variable, we lump them all together into a vector called Y, and we capitalize it. And so this will generally have 4 components for this example. There'll be NA, N sub D, which is our desired component, N sub U, which is the undesired one, as well as temperature. Right, so all of these are functions of volume. Presumably, as we go down the length of the reactor, these things are changing, right? Obviously, the outlet ought to be different from the inlet, but we actually want to know how they're changing along the length of the reactor. This one can generally be either a column vector or a row vector. Usually it's a column vector, but just because that way everything is a column vector. But for the examples that we're doing today, since we're actually going to calculate stuff with it, it's a little bit easier to visualize it as a row vector so that we can actually do some of the math. The other one, though, is a vector of our derivatives, so dy dv. This one will always end up being a column vector. So this will be a dna dv, dn d dv, and u, and finally temperature. Why does it need to be a column vector, or why can it sometimes be a column vector or row vector? Only because that's the way that MATLAB syntax works. If you had a different piece of software like Python or Polymath or Mathematica or something like that, they may not require it to be a column vector. That's just a syntax problem. And so each one of these are from a material balance or an energy balance, right? So we can evaluate each one of these from the material balance, which in your book is equation 7.1. And then the last one over here is your energy balance, right? And this is equation 7.2. If necessary, when we get to more problems with more components, so if you have more components, you just add the, usually I go like all material balances followed by the energy balance just because it's easier to keep track of them. One day we will have a pressure term, and so we will have additionally a pressure drop with respect to volume, and we'll have a special equation for this one. It's not an energy balance, it's not a material balance, it's actually what we call a momentum balance. But we're going to get to that later. So the nice thing is if we can establish how this works for 4 components, so 3 materials and 1 temperature, to add more and more components to it to solve more and more differentials just means to tack more and more things onto the end of it. So 4 is enough to kind of, it's like the physicists say, there's only like 3 categories of things. There's 1, 2, and many. Once you go beyond 2, it's really just kind of like an extension of 2. So it's just 1, 2, and many. The types of calculations that we would do if we wanted to do this numerical approximation, last time we had summarized in a table. And we can use exactly that same table, even though there's more than 1 component. And I had briefly mentioned this last, Wednesday or something that I had started. I had said, it doesn't matter if there's NA and NB or just NA or NA, NB, and NT. You can extend the calculation we were doing pretty readily, and that's what we're going to calculate today. So the method of solution by this numerical approximation can be visualized with this table, where over on the left we start with our iteration or step. Iteration is another word for step. And then as we go, we're going to slowly increment the volume. So we'll do everything in liters. I guess I might as well put the units in here. So our volume will be in liters. We will always have our y sub I old. And so that will be a vector, right? That'll contain 4 components, 3 material flow rates or molar flow rates and 1 temperature. And then we're going to calculate a change. So dy dv. And that will be another vector. So this will be a column vector. And then from that column vector, we will be able to evaluate a new y sub I, right? So this will be y sub I new. How are we going to do that? We're going to do that with the equation that we have right up here. So we're going to take exactly this same approximation and we're just going to apply it for every component that we have inside of there. So we're actually going to write the function that does that, so that you can see what a few steps of these iterations look like. And if you were to follow along inside of ODE 4.5 while it was doing its steps, you would see something similar to what we've got here. You'd see it a lot more than what we've got here, because we're only doing one calculation per step, and ODE 4.5 does like 6, because it's much better at estimating that slope. But I want you to see the general idea so that you have an understanding of why the local function is written the way that it is and why the output looks the way that it does. And along the way, hopefully, we'll kind of review some of the material balances. So the first row of this is pretty much always the same. It's always the initial condition. And so this is our sort of 0th iteration. We have not taken any steps. And so our volume is 0.0, right? We're right at the beginning of the reactor. An odd system of the way that we have the table is we don't define an old y or an old slope at this point, because this is the 0th step. We will only calculate those later. Our yi, quote unquote, new is just the initial condition. And so we said that from the problem statement, there were 18 moles of A coming in. There was no desired and no undesired, and everything came in at 400K. Right, so these are quote unquote our new values, but really these are just the initial conditions. And the first row always kind of looks like that. So initial conditions are here. And notice there's kind of an initial condition over here in the sense that volume always starts with 0. We never start our calculation from the middle of the reactor, right? Because we never know what's happening in the middle of our reactor. We only know what's happening at the beginning of the reactor. And so you can kind of think of that as an initial condition, but they're all lumped together as an initial condition. We know those values at the beginning of the reactor. So our next step in our very first iteration, right, if we wanted to take our step and we're looking at this plot, and we wanted to step away from an initial condition, which was over here, to this first point that's over here, right? How do we go from here over to here? We start from our initial condition. We define how big of a step we took. So I'm just going to arbitrarily pick 0.1 as our step size. So our volume goes from 0.0. I'm going to move these over a little bit in anticipation of needing a heck of a lot more room. 0.0. We're going to take a small increment of volume step size, right? We're going to go up by 0.1. Our old values just become the previous values of the new ones, right? So this becomes 18, 0, 0, and 400. And that's just taking what we saw previously, right? This is exactly what we had here, right? Just take the previous iteration's new values and move those down. Those now count as the old values. The trickier part, and the part that takes really all of the time, is writing this function. So what we need to be able to do is take all of this information, right? If all we know is the old values of all of our variables, NA, ND, NU, and NT, how do we combine those and put them inside of a function along with, if necessary, which it will virtually never be necessary, but it's there for syntax reasons, as well as the current volume that we're at, and find out what is our new slope. And that is the local function that we have to write inside of MATLAB. And so we're going to spend some time talking about that local function. But the key idea here is the local function only depends on the single value that you had before. And so I think often some of the problem with writing the local function is, why am I only calculating things based off of a single value of A and a single value of ND and a single value of NU and a single temperature? The reason that you're only doing that for a single value is because you're only calculating it based on these values, right? Whatever the previous set was is just one value for each one, right? An NA, an ND, an NU, and a T from the previous point. We don't care what happened 15 points prior to that, which is why it's only dependent on one value. And so what we have to do now is switch over and write our local function. And so we're going to do exactly that. If you've got MATLAB handy, we're going to spend a fair amount of time over there, but we'll switch back and forth to kind of update our table as we go. But we'll use MATLAB basically as a big calculator, which is that's all MATLAB is. So let's go ahead and switch over here to MATLAB. So I've got my sample set up right here. I'm just going to type in what my old value happened to be. So yi old happened to be 18, 0, 0, and 400. And then our question becomes, how do I write a function so that I can call that function and say dyi d, let's just call it dy dv, based on the old values is equal to some function of v, if I needed it, and yi old. I'm just going to call them y old. Right, that's my goal. If I can calculate what I've written there on line 3, so this line 3 corresponds to that part in red that I had written on the previous notes page, which is how do I calculate the slope, right? I need a function to calculate the slope. All I know when I calculate that function is the previous point's value. So all I know is 18, 0, 0, and 400, and if necessary, the volume. We can go ahead and add the volume as what is the current volume that we are working on. We might as well call it old if we wanted to, and that's 0.1. Why 0.1? Only because that's the step size that I picked. We don't get to choose the step size. ODE 45 will choose the step sizes for us. So we will never get to choose V old. It will be set for us. So this function is generally written as dy dv based on the old values is a function of the old values for v and the old values for y. Right? And then we're going to end it. So we can always start with this particular form. It's going to be a local function, so we need the function definition here, and we need an end statement at the bottom because this is a local function. You can make it a standalone function if you want, but it just gets confusing because so many similarities happen between problems that it becomes strange to have to start naming things in such a way that it's obvious what they are, but doesn't look like something else. So I recommend a local function. That next point that or the next line that we add on here is we are always basing everything off of the previous point. And so often it can be very easy, instead of talking about indexes into y old, to just sort of quote unquote extract those values so that we can work with them directly. So for example, I know within y old, they're coming in a following pattern, right? I know this pattern is NA, the next one is ND, the next one is NU, and the next one is T. Rather than have to index in and say y of 1, y of 2, y of 3, every single time I need one of these variables, it's often easier to extract them once at the very beginning, and then you can just refer to those values as we go. So the previous value of NA is NA old, and that is in the first element of Y old, right? It's Y old of 1. That is the old value of N sub A. Similarly, ND is Y old of 2, right? It's the second element inside of Y, and NU of old is equal to the third element of Y, and our previous temperature, the old temperature, is Y old of 4. How come it goes 1, 2, 3, 4 in that order that I have there? Because I picked it to be that way. If you don't like that, if you would prefer to switch them around and go temperature, molar flow rate, molar flow rate, molar flow rate, knock yourself out. It'll work just fine. I'm in the habit of doing this just because we sort of build up our examples as initially they're isothermal, and so I just tend to add the temperature stuff to the end. So this is what I mean by often the first thing that we do is sort of quote unquote extract those variables. I am inside this function and I would like to be able to calculate things based on the old value of NA, old value of ND, old NU, and old T. Once you've got those extracted, I usually suggest that you work from sort of work backwards, right? Work from the end of the script to the top, or end of the function to the top of the function. The reason being, after you write the material and energy balances at the bottom, it becomes sort of a matching problem, right? If I need to calculate the stuff down here on the bottom and those variables don't exist, they have to be added up above them. The only ones that exist when the function starts is the old values, right? Which we have just started with right here. And so the last line that I tend to put in here is the slope. So dy dv old is this column vector dna dv old dnd dv old dnu dv old dt dv old, right? This is our column vector. I'm now in a point where I can start to work backwards, right? What I start with, the only thing that I start with is the value of the points at the previous step. That's all this function knows. So any calculation that I do after that, if it needs a parameter that is not one of those, then I have to define it. And I have to define it inside of that function, or the function won't know that it exists. What do I have to calculate? I have to calculate all of the slopes, which are here. Notice that I've used the word old a lot, right? Old meaning it was the point right behind us. It gets a little bit tedious to carry around the subscript old everywhere. And so you will usually see me not use the word old, which is easy. You just go through and delete all of the subscript old on here, which I'm just going to go through and do really quick. Because everything inside of the function is evaluated at the old value, it kind of becomes a little tedious to keep writing old everywhere. So I just delete it. If it helps you to remember that these are all the old values, just add a comment at the top, which I'll do here in a moment once I get rid of all of these old values. But I only wrote that because I wanted to remind you of what we are calculating, which is these values based on old values of like NA and stuff like that. I'm going to leave Y old up here, actually. There we go. I'm going to leave those outside of my function because I don't need those yet. So these, if you wanted to add a comment, all of these values that we're doing in here, they're being evaluated at our old point, right? The point that we had previously calculated. And so we're eventually going to use these to update things. So working backwards, what do I mean by working backwards? I usually recommend that you write the material imbalances and energy balances first. And if you write them in a fairly general way, it will reinforce that pattern to you that these all kind of look the same every single time. So for example, dNA dV is always going to be equal to RA, right? Where RA is going to be the slope that we've got on here. Y of 1 isn't defined because it's still Y sub old. It looks like it'll be okay because I don't have any more olds inside of my function. The units on this will always be something like an amount per volume per time. And so most of the problem definitions units were moles per liter per second. And so I'm just going to assume that these are all moles per liter per second. And then I'll force everything to match those units as I go. Similarly, the rate of change of D is the net rate of D, which is also moles per liter per second. And Dn undesirable is Ru, and that's also moles per liter per second. And then finally, we need the value of, or an expression for the energy balance, which is equation 7.2. And that one's usually a little bit nastier. dT/dV. In the numerator are two terms. There's a Q minus a sum of R times DH. And then this is divided by the sum of N times CPI. This has to come out in, again, a fairly weird system of units, which is going to be a Kelvin per liter because you're sort of moving along in the volume. So dT/dV has strange units on here. Just to you can use vector notation to write these if you want to, but just to practice sort of expanding these so that you can see what they look like and see what the subscripts look like, I'm going to actually write these out. And so the first one is R1 times DH1, and the second one is R2 times DH2. Right, so the rate of reaction 1 times the enthalpy of reaction 1 plus the rate of reaction 2 times the enthalpy of reaction for reaction 2. That's what the sum looks like. And then similarly, the moles of I times CPI summed up will look like Na times CPA plus Nb times CPB plus Nc times CPC sorry, it's not A, B, and C. It's desired and undesired. See, you get into those habits. Right, and so these are very general expressions. So the majority of the problems that you're going to work on, assuming that they follow the material and the energy balance, are probably going to need expressions that look very much like this. And so if you can get into the habit of writing those when you get started, you've now got yourself a good start, right? You can actually begin to rely on MATLAB's error checking to decide whether or not you've written everything that you need. But more importantly than that, these are written in such a way that they look very, very similar to the way that they do in the book. So for example, the comparison here is equation 7.1. If you go flip over to equation 7.1, you will almost be able to read out loud from the book that it is the same thing as what I've written right here, right? dNA dV is equal to the net rate of RA. And so this gives you a link between the way that the equations look on the paper versus the way that they look inside of MATLAB. And so that's always a good way to avoid mistakes, is to try to make the code look similar to the book or the equation, even if it means adding a few extra lines. It's not going to slow down your computation at all. So don't worry about that. We're now in a position where we have to go backwards, right? I've got obviously the NA, the ND, the NU, and there's no temperature on here, but those already exist as inputs because they're being used from the previous value. But I don't have RA, I don't have RD, I don't have RU or Q or any of these rates or anything like that. And so now I have to start building these codes or building these segments of codes together until they match. And generally that goes sort of bottom to top. As you'll see in a moment, I tend to organize my code in a way that we kind of build them together, right? Build from the top down and from the bottom up. It's kind of like bridges are built that way, right? It's not just from one side all the way over. It's two sides coming together, or tunnels are usually two sides to coming together, not just bottom to top. But you always start sort of at the bottom. At least I do. So let's add some space here, and let's do a quick example. What if we had to write the net rate of A, right? I want to focus on this one. I know I need that value, so I'm going to start writing it. I'm going to put algebraic expressions here, and I'm going to add any constants up here. That is entirely just the way that I want to do it. I like dividing my code between differential equations, algebraic expressions, and constants. It's just how I am. You could lump them as like material balances and energy balances if you wanted to, whatever form that you want. But I know I need RA, right? And RA is going to be the net rate of A. So if you look back at the rate or at the expressions we had an A goes to B, but A goes to D, and also a 2A goes to U. And so the net rate of A is the sum of each of those rates times the stoichiometric coefficient of A for each one. So that's going to look like a -1 times R1 plus a -2 times R2, right? That's going to be my net rate of A. Notice I'm trying to keep it very general, right? I haven't defined R1 or R2. This way that I can go back to line 19 and say, did I at least write the net rate of A correctly, right? And that's a separate problem from, did I write the rate of reaction 1 correctly? Now I can write the rate of reaction 1 as K1 times CA, and the rate of reaction 2 as K2 times CA squared. Both of these are going to have units of moles per liter per second. And I've sort of, it's almost like I've shot myself in the foot, right? I tried to define RA, and all I did was introduce new variables, right? I introduced R1, I introduced R2, great. Then I went and defined those as more algebraic expressions. And it's like the problem just got even worse, right? I've now introduced K1 and CA, K2 and CA squared. It's like they just keep building and building and building. But that's the approach that we're going for here, right? We're trying to keep them looking the way that they do in the equations that we have available to us in the book. And we're trying to build them backwards until eventually we can actually calculate these things. So for example, I know that if I want to work on CA right here, CA is equal to NA divided by V. And this will be moles per liter. I got a little bit better, right? I defined a variable and I at least didn't introduce more variables because I defined a variable and then introduced a new variable. So, you know, I sort of stayed level. I need to still define more things because I define them as NAV, but at least I know what NA is, right? How do I know what NA is? It's the previous value that I have up here. And so now I have to add another algebraic expression for V, which is V0 times NT divided by NT0 times T divided by T0, and then leave off the P because the P is not there. And again, I just kind of shot myself in the foot, right? I defined one variable, which is great, but in so doing, I defined V0, NT, NT0. T's okay. We've got T, right? That's up here on line 13, but we don't have a T0. And so now we have to go through and define all of these as well, not to mention the K's. And so what I want you to do is take, it's 3:37 right now, go up until about 4:43. So take about 6 minutes, see what you can do to just keep working on RA, right? So keep filling in K1, K2, and all of these values and see how far you can get. And then in a moment, once we've got it, I'll post, I'll just copy paste into here so that you can kind of compare the two. And then we'll look at what the function is doing afterwards. So take until 3:43 to complete, I'm going to put complete in quotes, complete RA, right? Just keep filling in values for RA until you think I've got everything completed so that I could at least calculate RA if I needed to. Yeah, the completed code's all going to get uploaded, but I want you to try practicing it right now for a couple minutes. We'll put on some sneaky adventure while we're doing this too. Feel free to ask questions in the chat as well. Yep, K1 and K2 are functions of temperature, so you'll have to adjust those. The heat capacities are given for all of the components, so they're all equal to 65. And that's not specific to a reaction. That's this component has heat capacity regardless of what reaction it goes into. About another minute and a half. About another 30 seconds. All right, let's take a look at what I got here. So if you missed one of these, don't worry about it. It's not the end of the world. It's not a timing contest. We have no exams. So it's not like you're going to have to write this in 50 minutes or not. But what I want you to look at is compare whatever you came up with, either in your head or as you were coding, with everything that needed to be there, and just check whether or not it seems like, yes, I was aware that that needed to be there, or I was not aware that that needed to be there, because we're just going to fill in the rest of this code here in a moment. So we definitely need our two reference conditions for K, and we know they're at 315 and 280, and their activation energies, all of which were given in the problem statement. The constants portion of the script tends to be stuff from the problem statement. And then we've got a couple others, right? Our inlet temperature, our inlet molar flow rate, it's pure A, so the total is just A. The volumetric flow rate is 5, and I defined a gas constant. And then my algebraic expressions, I adjusted both K1 and K2 for temperature, and notice that I used different reference temperatures, right? Because we knew the two different Ks at two different reference temperatures. We can calculate the total number of moles anywhere within the reactor as just the sum of Na, Nd, and Nu. And then from that, we can calculate everything else that we've got. And so this is what I mean by you sort of start at the bottom with a fairly narrow set of equations and then build yourself backwards and then build yourself down at the same time, right? Backwards and forwards until you kind of meet in the middle and everything is defined. All of them have to be defined. And so frequently these pieces of code can get rather lengthy if you're writing them with this particular style. So this code I will post on the website. So don't worry that I just posted a bunch of these in here all very, very quickly because I just have 5 minutes left. So I want to demonstrate how do we actually solve stuff. And so the other stuff that I just posted in here were the rates of the other components, as well as the energy balance terms. So if you don't have those, don't worry about it because I just want to show you how the local function is used. The feeling of populating that local function is very much like populating RA. It's just defining stuff until everything is there. So how do we use it, right? The idea, I'm just going to bump the function off of here so we don't even have to see it anymore. The idea is that we want to be able to calculate the slope. And so if I change this so that we can actually run this thing, hopefully I haven't made any errors, we can get the examples out down here, right? So what I did was I used that function, the one that we just wrote, and I passed to it as an input the old volume that we were at, as well as the old value of Na, Nd, Nu, and Nt. Remember, that was exactly the same input that we had defined here, right? Take any V, take any set of Y, and output the corresponding slope. These values that just printed out here are the corresponding values of the slope. And so those would go into that next element of our table, which we can add at least a couple elements to real quick. So we just used our local function to calculate those values of the slope, right? And so those would end up going in over here. So let's switch, delete these. We just used that local function, right? We just said, use the function, and we calculated, if you looked at the stuff that came out of the MATLAB script, we calculated some numbers, minus 0.0078. Oh, sorry, there were 3 zeros there. 0.00056, 0.00011, and 0.0523, right? And these came out as a column vector, again, only because that is the style that MATLAB needs them. In order to go from that slope over into our new value of y, we just multiply the two together and add them to the previous one, right? So we apply this big highlighted equation, which if we wanted to do inside of MATLAB, I'll show you the code in a minute, but the result would be, it's a long set of numbers, 17.9999, 0.0001, 0.0000, and 400.0052. That's all one column vector or row vector. I just ran out of space. So notice a couple of things about the comparisons here. The very first element of our slope was negative. That means the amount of A is decreasing. And sure enough, if I calculate the amount of A compared to the previous one, I went from 18 to 17.9999. Ideally, those will be very small, right? Because I'm taking very small steps to keep my accuracy high. And similarly, our last entry here is how is the temperature changing? It's going up, right? It's an exothermic reaction. That's good. It should be going up. And sure enough, our second temperature is just ever so slightly than our previous temperature, our new temperature. And so those are good, right? These are sort of sanity checks that you can ask MATLAB to perform for you when it's just getting started to figure out why it is that the behavior is the way that it is. In order to continue the calculation, we don't change very much, right? We can use the code that we've got and repeat, right? We can take this one and send it over to this column, use our function to calculate a new slope for everything, and then use our new slope values to calculate our new point values, right? And so this would correspond to our second iteration out at 0.2 liters. We'd have to calculate all of these, but we just did that, right? Those were the old values. Use our function. So this is our MATLAB function, our local function, to calculate the slopes, and then just multiply those by the size of the change and add them to the previous one to get the new values over here. That becomes really tedious, right? To do this iteration over and over and over again. It's not difficult if you want. I should say it's not difficult. It's tricky, right? The tricky part is you need to use a for loop in order to do it, and nobody wants to use for loops. I've noticed most people don't like using for loops. So how do we do that? We ask MATLAB to solve it for us, right? So instead of using a for loop, we say do this at the function from 0 to whatever range we need, starting from our initial conditions, which are y old. The output of that will be the two things that we just calculated. And so this VSOL will be those volume points that we had, and YSOL will be that matrix of all of the values that we were slowly calculating on the outside. So YSOL and VSOL, if we switch back over to our notes page real quick, and I know it's 3:50, so I'm going to stop here. These values over here, if you look at the matrix of values for yi new, that's all of those values, right? So if I take this big matrix of values, so the first row is the first iteration, or the 0th iteration, the second row is the first iteration, et cetera, et cetera. This is our YSOL, and our VSOL is all of these values over here, right? So we're going to get a vector over here and a matrix over here. And that is exactly what ODE 4.5 is doing. It's just doing it much more efficiently than what we just did, which is sort of one calculation at a time. But I hope this lecture has showed you why are we doing the calculation one at a time. It's because we're just ticking our way up on the slope. So this would be the completion of the problem, right? We've we've solved it with ODE 4.5. We've written our local function. If we had to, we would plot it because that's our profile. So that's 351. I want to wrap it up because I know some of you might have lecture. I will absolutely post this script, so you'll be able to review everything that's on there. But challenge yourself and see how much of that script you can come up with, and then compare it to what I've got over here. All right, good luck, everybody. Projects posted for midterm 2, and we will see you on Wednesday. Stay safe out there. We'll throw on some sneaky adventure too, so we don't have to sit in silence. And as usual, you know, I'll stick around and answer or questions for anybody who can hang out afterwards. Oh, that's a, let me unmute all of this. Chat with, oh yeah, okay, good, it's already unmuted. There's a question in chat, what's the significance of the V in the local function? It's one of those terribly unsatisfying things. That's the syntax that MATLAB needs. It needs to know what was the independent variable and what was the dependent variable. And so you put the independent variable first and the dependent variable second, even if you don't use them. You just leave them there as sort of like placeholders so that MATLAB knows where to go to look for each one. There are ways around it, but I don't suggest that you look for them and just use that version. Yes, it does matter which one comes first. The first output will always be the vector of independent variables. So if you switch it and call it YSOL and then try to plot it, it's going to be a nightmare because you're going to have a matrix of volumes, quote unquote volumes. So yeah, they have to come out in the order of independent variable first, followed by dependent variable second. Yeah, for the homework, you can just plot it and estimate it from the plot. That's fine. If you want to get fancy, there's some stuff in chapter 6 about how you can ask for a solution at a particular point, but you don't need it. You can just plot it if you want and estimate it from reading off the plot. There's a question in chat, will mistakes from the previous project impact our next one? No, I've posted if you're worried about it, I posted a solution for the rates function, and you can use mine if you were worried about it. You have to modify it for the next one. So if you're confident your previous rates function was accurate, then it might be easier for you to modify your own function than to try to sort of get into my head the way that I was writing it and modify mine. But you can use either one. And we won't like continue to regrade the intro in the background and stuff like that. Although there's a comment on the syllabus, it does have to be complete by the time that you turn it in. So you have to make an attempt at everything. You can't turn it in with a giant blank section. So you got to have something in there. Yep, they keep building on each other. You can kind of visualize where we're going, right? We started with net rates because that's what we had covered in the first couple of weeks. The midterm project 2 is model it with a CSTR. The final project will be finish it up with a model as a PFR. So, I mean, if you're super ambitious and have no other classes to work on, you can kind of ballpark where we're going and just switch the model out from a CSTR to a PFR. But I can't say I would start doing that. Do the CSTR first. All right, pretty much quieted down, so I'm gonna go ahead and stop recording this. Dink, dink, dink. Stop recording. Yes. See you Wednesday.